Hello, everyone. Thanks for joining and welcome to our webinar on integrating an INS device with a 3D LiDAR. My name is Sam Soliman. I'm Senior Support Engineer here at OXTS, and I will be moderating today. The webinar will be presented by Jacob Amaker, Product Engineer for the LiDAR Survey Area at OXTS, and by Dieter Gabriel, Marketing Manager for Europe, Middle East, and Africa at Velodyne LiDAR. So the presentation will go through a bit of LiDAR and INS technologies, the many applications where these technologies can be applied, and we will have also examples of this and some use cases. And obviously, we will go through the importance of having an INS coupled to a 3D LiDAR in order to have the best georeferenced LiDAR data. If you have any questions, then please submit them using the questions chat box. We will try to get you all the answers, but if we do not manage to answer your questions during the webinar, we will reach out to you and provide you with the answers via emails following the webinar. So that's it from me, and over to you, Jake.
Thank you, Sam. So as said, my name is Jacob, and I'm the product engineer here for OXTS Survey and Mapping, and I'm glad to be joined by our friend Dieter from Velodyne. So, yeah.
Yeah, hello everybody. Warm welcome from my side as well. I'm Dieter Gabriel. I'm doing the marketing for the EMEA region, and I have to say I'm really pleased to participate in this webinar today. You know, it's the first time that OXTS and Velodyne do a webinar together. Indeed exciting.
Yeah, so let's get started with the presentation. So we are Oxford Technical Solutions, as many of you will know, and we have over 20 years of experience in getting the best navigation data using our iconic red box INS devices. You'll perhaps already know that INS devices are commonly paired with LiDAR to get the highest quality survey point clouds, and we'll talk much more about that. We've become, over the years, the market standard in the automotive industry. So the chances are that the car you drive was tested using our equipment. And we're now the only INS manufacturer to provide a data-driven bore site calibration solution for use with LiDAR data. And we'll talk much more about this. We have several products that we offer, including these two that you can see on the right here. So the Survey Plus is our flagship navigation product, especially good for land survey mapping with LiDAR. And there's also the XOEM, which we have for integrators who want to build their own products. And OXTS will shortly be becoming automated with Velodyne. And so you can expect much more collaborating between us and Velodyne in the future. So more content like this, and more technological work together. So do keep an eye out for more webinars and more collaborated social media work. So over to you, Dieter.
Yeah, thanks, Jake. Okay, a little bit about Velodyne, just brief intro. We've been around for quite a long time now. Our founder and owner, David Hall, invented real-time surround view LiDAR systems back in 2005. At that time, LiDAR activities were part of Velodyne Acoustics. And since then, a great success story developed. We started commercial production back in 2007, and we are indeed proud of where we are today. Here you see our global presence. I'm just talking from our Europe office near Frankfurt. Today, we have an incredible number of customers worldwide. We not only work with most major automakers, but also with an impressive variety of different technology sectors. Meanwhile, our company has been inventing, producing, and testing state-of-the-art sensors for more than 13 years. And with our current range of LiDAR products, we do much more than automotive. And I'd like to stress this, it sets us clearly apart in the LiDAR market because nobody has long experience, nobody has sold more sensors in so many different industries. Our portfolio of sensors addresses AV and ADAS, robotics, industrial equipment, machinery, UAVs, drones, agriculture, security, traffic in smart cities, well, and mapping in general, and for a huge variety of special applications. And to serve this huge variety of different user segments, we have a full range of sensors giving our customers best-in-class performance. If you would like to learn more about our sensor product line, please reach out to us. I don't want to go into more technical detail at this point and would like to share a bit more information about 3D LiDAR in general and possible applications.
Yeah, so sorry, we got a poll open now. So what applications are you most interested in? So we want to know exactly what you guys are up to.
I'm just giving people just slightly some more time. Here we go.
Cool. Thank you.
So yeah, we can see that there's a lot of people interested in digital mapping. There's a lot of geographic surveying going on and some infrastructure monitoring with quite a lot of asset management and other. So a huge range of different things, but digital mapping being the clear winner there. So over to you, Dieter.
Okay, thank you. Just a few basics about LiDAR. Our LiDAR technology uses eye-safe laser beams to create a 3D representation of a surveyed environment. LiDAR offers strong performance in a wide variety of lighting and weather conditions. Let's have a closer look at it. First, let's think about what does it actually mean to scan an environment in 3D? We see here a walking person just as a dot. That is not very impressive, isn't it? But watch out. Let's switch on now one of our 3D multi-beam sensors. Wow, look. So I think this speaks volumes. And it's not yet the mapping approach, no georeferencing. We have here just real-time data, just a raw data stream. And such a multi-channel LiDAR scans its environment with billions of photons per second at 360 degrees in order to completely see the surrounding world. It highlights objects and makes them recognizable and shows movement on whatever platform you put it to. LiDAR can handle object recognition of both non-stationary and stationary objects, and as its own light source, can even see at night. Here's a nice example to illustrate the benefit of a true 3D LiDAR once more. Look what happens when you scan a row of houses with a classic 2D laser. The red object here shall indicate a parked car. Our mapping platform now moves from left to right, and you see only two sides of the buildings are visible in a single mapping pass. And with obstacles, you can get pretty affected by shadowing. You're gonna lose data. Now, the same approach using a 360-degree LiDAR. Look what happens. Just with one LiDAR in a single mapping pass, you get significantly reduced shadowing, and you can capture three sides of these buildings. You get more data. Literally, you boost your mapping quality to the next level. This benefit is also demonstrated in the following example, which highlights further our calibrated reflectivities. At first glance, you may wonder what makes this picture spectacular. Well, look how we captured a lot of retroreflectors. So what is special here? Think about the number plates of the parked cars. In this example, you get the signals from these reflectors. All four the plates are basically positioned perpendicular to the trajectory path of the mapping platform that in this example was moving straight from right to left. And like in the example before, we capture data by kind of looking back. So we get all these interesting objects we like to catch, we get them mapped. How good retroreflectors can be captured, you see in a real life data set. This data is from our most advanced LiDAR sensor, the Alpha Prime. Look at how the traffic signs, lane markings, and other details are now depicted. The richness of details also from an inner city scan, you will see soon. And this is, again, just real-time data, not yet applied a mapping approach, not georeferenced with a good INS, as you will see immediately in further use case examples. So impressive. You see the details on the van, you see the reflectors, and now we come to the inner city part. You see the trees, you see the number plates again, pedestrians, cyclists, everything in enormous details. By the way, just a quick info. Our famous HDL64 sensor has become an industry benchmark as reference sensor, namely for automotive. And with the Alpha Prime, we more than continue this success story and offer the most advanced 3D LiDAR perception technology. There are now great upgrade opportunities from the HDL64 to the Alpha Prime. So should you be interested, please contact us. Well, there are manifold LiDAR applications, surveying applications from coastal monitoring about ADAS, AV, construction, mining, pipelines, up to security, military-related operations, forest crop management, and a lot of things more. Yeah, as already stressed, there are almost endless application examples. Just have a look at that here. Nice example for canopy mapping. It doesn't matter if grassland, shrub, or dense forests. Here is a forest mapping example. And you easily get the overall canopy density, tree locations, or crown diameters. Next slide, press. Yeah, look at this. So we have the canopy level. We have the location of any specific tree caught in that area. Next. And we get the specific information we can derive out of the data set. Yeah, and by the use of 3D LiDAR return modes, you can derive information about different surface levels. In our example, it's the actual ground, the terrain level, distinguished against the canopy height. So here in that example, you have the last return to identify the ground, and the strongest return you get usually from the canopy level from the top of the trees. This is a pretty nice example how such evaluations work. Other examples, think about maritime use cases. You can combine, for instance, above and below water sensors simultaneously and use an INS both for LiDAR and sonar sensors, just like in that example. Or here you see scans of port, waterways, environments. Again, you can combine maybe with an underwater sonar and you get a great 3D coverage above and subwater. And in all these cases, you look at process data. And we should not forget to talk about the difference between raw and georeferenced data. The blue image here illustrates how the raw LiDAR data output looks like. And to come to results as shown in the black and white pictures, you need to georeference the data. And this will be the major part of the following slides. So you end up with such nice mapping data representations. And here's another great example. So we see here a zoom into a data set of a forested valley area. It's very impressive, I think. So do not wonder about the colorization of this image example. This represents not as usual different reflectivities, but in that case, it's linked together with height information. Yeah, Well, and over all these cool examples, we should not forget that one of our main technology drivers clearly remains automotive. So we can do more than mapping treetops, sorry. To conclude this, have a look at these impressive data sets from our UltraPAC and from the Alpha Prime. So really, possibilities are endless indeed. And I'd like to hand over to Jacob again.
Yeah, thank you, Dieter. The technology from LiDAR just has huge potential. So we're going to have another poll question here before we go on to some more information about the INS. So we've seen data from, I think, UAVs, cars. I think some of those may have been from light aircraft as well. Perhaps some handheld LiDAR as well.
Yeah.
So we're seeing a lot of car users, especially, but also a surprising amount of handheld LiDAR surveying. Okay, so it seems cars are the winner there. If I just share that with you guys. So you've told us that the car is your principal choice, and then followed by UAV and handheld LiDAR mapping. So thank you for that. So we'll go into more detail about INS technology, how it works, and how it gets the navigation data for your LiDAR. So an INS combines an IMU, Inertial Measurement Unit, and GNSS, Global Navigation Satellite System. Now, GNSS isn't necessary as there are alternatives, but these are typically for more niche cases and can't replace GNSS as the principal INS technology. So an example might be some Doppler velocity device if you're working underwater. The IMU is able to measure the intrinsic motion of the box or vehicle, and the GNSS gives the INS its absolute position on the Earth. And these really come together to make an INS much more than the sum of its parts, as they each play to their own strengths and compensate the other's weaknesses. In an OXTS INS, the raw data is intelligently combined, which we'll talk more about later on, to get GPS-grade time accuracy with high precision position and orientation information with an absolute reference frame anywhere on Earth. So how it works, how it actually makes things possible. Again, it gets the position information primarily from the GNSS, and this is kind of tempered by the IMU stability, and the orientation information is given by the IMU. So it will get some heading based on where the INS figures out it's going towards, the direction of the device when it's moving, and you can get orientation, the roll and pitch from this as well. So LiDAR is accurate to several centimeters, and so your navigation position accuracy should also be on that order, but you also have to account for angular inaccuracy over a distance. And so you can see that with this rough calculation here and these diagrams. So you can see the effect of position inaccuracy will slide your points around from where they should be. You've got angular inaccuracy, and you've got a range inaccuracy from a LiDAR device as well. And these all add up, and you have to take these into account if you're looking to make a point cloud with a specific accuracy value. So you've got this rough calculation down at the bottom here, and you want the best INS device if you want to get the best precision in your point cloud, of course, but something you have to really consider is the angular orientation precision, because over a distance, the further away you're looking, the more of an impact that's going to have. So we've got another question relevant to that, and that's at what distances are you likely to survey objects from? So we're looking at the higher values, it seems. I'll share these results in just a moment. But yeah, it looks like the higher distances are what you guys are trying to survey. And in that case, you're going to need the really high orientation values. Okay. If I just share those with you now. So you can see the highest over 50 meters we're trying to survey. So if you imagine you're multiplying roughly your orientation imprecision by 50, your points are going to be moving by about that much if you had the imprecision in radians. Okay. So a question that we often get is, why can I not just use a GNSS receiver? And there are several reasons for this. So first of all is that you need orientation data if you want to build up that 3D point cloud image. And to get this with GNSS, you would need a third antenna for a third axis, which is often impractical, and the precision not often high enough. So we just saw how important precision it really is when you're looking at orientation. And also, when you lose sight of satellites, you lose data. So with just GNSS, you're just going to drop out data completely. You could get a IMU, an external IMU, and put them together. But an INS would combine the data intelligently to get the very best navigation data. Whereas if you just had a GNSS and a standalone IMU, you're not going to get that high quality. So how it works, the actual LiDAR technology, how it works. So over to you, Dieter.
So it's not rocket science. Georeferencing LiDAR data means a Velodyne LiDAR sensor can synchronize data with precise GPS supplied time. Synchronizing to GPS supplied PPS signal provides here the ability to compute the exact firing moment of each data point as required by georeferencing applications. So the GPS INS device needs to be configured to issue PPS signal in conjunction with a once per second NMEA GPRMC sentence, as shown here in the graphics. And in order to come to precise mapping data, you need to convert the original file structure, in our case, a packet capture file, to a georeference point cloud format. So this is the basis to get what we highlighted before. So shown here in the difference from the blue raw data image to that illustrated here in black and white, accumulated and georeference data. So the data provided by a LiDAR sensor in a raw file is measured relative to the sensor's reference frame. You see here in the picture on the upper right part of the image. So that's markedly different from a point cloud file where the data points are referenced to a real world coordinate system actually. So the coordinate system could be an earthframe, latitude, longitude, elevation, or whatever convenient reference frame. So processing the raw data into a point cloud is what we call georeferencing. And in the georeferencing, you take into account both the sensor's position in X, Y, and Z, and the orientation of the measurement platform in pitch, roll, and yaw for each measurement. So knowing these just 6 values allows you to apply the appropriate mathematical rotations and translations to place LiDAR data into that single coordinate system. So at the end of the day, that's it. And so to build a LiDAR point cloud, you need to move the sensor in space to scan all parts of the scene. And you have to consider that you use or that you derive data relative to the own position of the sensor, and therefore you must account for the sensor's position and orientation at each moment. And by knowing this position and orientation of the sensor, you finally can translate the LiDAR data mathematically into a single reference frame and generate your point cloud model. This is what we understand under georeferencing the LiDAR data, and the technology for this comes again from the INS experts.
Yeah, so briefly, this is how the coordinates of points are calculated. So first, the INS acquires its position from GNSS data that is refined by IMU data, and this is in a particular coordinate system, which is converted to simple Cartesian coordinates. The relative distance and orientation from the INS to the LiDAR, as you can see in this picture here, is then added onto this. And then finally, as Dieter has been explaining, the coordinates of points from the LiDAR's point of view are added after being converted from polar to Cartesian. So you've got this very simple flow of getting the final coordinates of points. So here are some examples of why GNSS is principal technology. So on the left, you can see SPS, GNSS position mode, and on the right, you can see RTK. So these are, if you're unfamiliar, two different modes of GNSS. A lot of surveying is done with just SPS mode, which is absolute accuracy on the order of 1 meter. But on the right is RTK mode, which has an absolute accuracy of about 2 centimeters. And this is what we offer with an INS. And you can see the difference here. So what's happened here is a vehicle has done a LiDAR survey going down a road, and then it has turned around and come down that same road. So if you focus on the lamppost in the middle, you can see that the lamppost has moved, supposedly, in the SPS position mode, whereas in RTK, the lampposts are overlapping. And so you can see that with RTK accuracy, you can survey the same area again and again and add to your data instead of essentially ruining your data by adding more lampposts where there aren't any. Here's another example. So the importance of the IMU. So you can see this fence line with a low orientation accuracy, and then on the bottom, a high orientation accuracy. So this would be taken by two different INS devices with two different IMUs with the same LiDAR scanner. And you can see that the higher orientation accuracy can see the fence to a finer precision than the lower orientation can. Now, here are one of our processing methods that we have at OXTS. This is called advanced smoothing. So this will take your INS data and intelligently smooth it. So you can see on the left, there are some jumps. So if you look at the white lines in the middle of the road, you can see that there are some jumps in the data, whereas on the right, it's completely smooth. And so if you're doing something like object recognition, these jumps in the data can throw off any computer trying to identify an object. And so having this advanced smoothing will account for that. Here's another feature that we have in our processing. So this is advanced slip. So this is particularly for land vehicles. This will essentially help the INS lock on to the heading direction that the INS is going. And so you get a much higher proportion of time being in the, being in the higher precision modes and with a higher accuracy. And finally, there's another one of our processing methods called GXIX. This is our proprietary tightly coupled navigation engine. And this will take raw GNSS data and look for single satellite solutions. And the end product that you get out of this as a user is that you have more time during your survey in the highest precision modes, and if you ever drop out of data, drop out of satellite view, you'll get that position lock much quicker. So I'll now go through our bore sighting solution. So we offer at OXTS some georeferencing software, and part of that is a bore sighting calibration. So a bore sight misalignment is a problem that you get with a navigation device and a surveying device, such as a LiDAR. And it's analogous to, say, a gun barrel and gun sights. So you need to calibrate the two, otherwise over a distance, the two lines of sight are going to diverge. And so you get the misalignment when you don't know precisely the angles between the two devices. And a tiny imprecision in these angles can really affect your point clouds, as we'll show you later on just how small that angle can be. And to measure the angles precise enough, so you need about 0.1 of a degree to get that precision that you need. And that can be extremely difficult with, say, doing it by eye, or even doing it with a CAD model or something like this. And so you really need this data-driven technique to calibrate your angles between the INS and LiDAR. So the reason that it's a problem is if you look at this black rectangle here, if you've got this object in reality and you've got a vehicle with a LiDAR with a slight bore sight misalignment driving from left to right, it's going to view that object as, say, that red rectangle. And then it's going to come around and turn around and view it from the other direction. And then you're going to get a distortion of that object in the opposite direction. And so you'll get that blue rectangle. And so in your final point cloud, instead of the crisp black rectangle that you're looking for, you'll have an overlaying of the red and the blue. So here's an example. So this is some point cloud data that we've got from a UAV some 30 meters above. And this is before bore sighting. So there's a misalignment between the LiDAR and the INS. And you can see here that the point cloud is quite unclear. And you wouldn't want to really give a customer this if they had asked for a survey. But after bore sighting, so the same raw data, you can see that instead of, if I go back, you can see there are two cars on the right there. Instead of two cars, you now clearly have one car, and all the details in the picture are much clearer, and you can actually identify objects. So this is the same data, but as Dieter explained earlier on, it's been filtered by retroreflective points. So if I look back now, so what you're looking at here are these two targets, the two bright yellow targets. So this is before bore sighting from the same raw data from that UAV flying once over it, let's say south, and then turning around and coming back, and let's say that's north. So this is two passes of the targets, and you can see the bore sight has shown, let's say that red rectangle in the example that I was showing earlier is so far diverged that you've got some double vision going on. So you can see two of the same object. And after bore sighting, you've got the crisp shapes that you were after. So not only do you have one shape, but also the shapes are much squarer, as they should be. These are square targets, and also they're much fuller. Here is another example. So this is again going down a road and then turning around and coming back. So what you're seeing here is a cross section of a road. So on the left, you've got a building. On the right, you've got a pedestrian there. And you can see quite clearly here the linear relationship between that imprecision in angles and distance, and how the two point clouds are diverging over distance, so the red and the blue. But now after bore sighting, they align perfectly. And so you can, again, survey the same area and add to your data instead of ruining it. And here is a final example with some angles. So example angles that you might have. You can see that the lamppost on the left is not in the right place. There are two of them to start with, and the angles that can give these kinds of differences are quite small, and you wouldn't be able to measure them typically by eye. So this would be something on the order of half a degree, something like that. And if you're viewing objects, this would probably be 20 meters away, I think. And you can see already that you're going to get double vision in some objects and distortion and all these problems. So we can quickly go through a case study using both a OXTS INS and a VLP16 LiDAR. So this company, Drone Zone in Romania, build high quality drones and wanted a LiDAR scanning option for their customers. They chose to use an XNav and a VLP16. The reason they chose OXTS is that they needed an INS that was highly accurate and could be carried on a drone, and that's easy to use, and they could trust in the quality of the unit. They also needed minimal work to set up on their own side, so we provide the georeferencer software, so they wouldn't have to make that themselves. And they chose the VLP16 because it is, Velodyne are the industry leaders here, and they are reasonably priced and easy to source. So the challenge was to get the best value for money INS LiDAR solution for most drone survey applications, and that would be minimal hassle when they come to OXTS as a solution provider to seamlessly integrate the LiDAR unit and their INS. And so what they wanted to do was survey 45 kilometers of road with their VLP16 device and to get an accurate point cloud as the outcome. So the XNav VLP16 package that they use saved them a lot of time in the field, and that's not to mention even the time in preparation and also the processing that they've saved. So they don't need to put the LiDAR data and navigation data together themselves because of our georeferencer software. And it gave them the flexibility, particularly with the boresight solution, to use their package on any vehicle. So they could put it on a drone, and they could put it on a car, and also handheld. So you can check that out on our website. So we've got another question here. So which statement best describes where you are on your mapping journey? So we just want to get an idea of exactly what you guys are up to. And if you're just looking to learn, or you're trying to get into the market, or you're already an experienced surveyor, we're just looking to find that out. Okay. If I share that with you guys again, you can see that there are a lot of people looking to learn, a lot looking for a navigation solution, and quite a lot of you are already surveying, with some of you just investigating the market and looking to purchase both the surveying and navigation equipment. So as a summary, we've seen how LiDAR has huge potential for surveying applications, and how INS technology gets the navigation data that makes that possible, with Velodyne and OXTS at the forefront of these technologies. We've seen practical examples of how these technologies can be brought together easily to create high quality point clouds and how they're used effectively in the field. We've seen the importance of getting the highest quality navigation data and also of bore sighting when using an INS LiDAR package for surveying. And we will now have time for some questions. So I hope you've enjoyed our presentation, and thank you a lot, Dieter, for all that information about LiDAR.
It was my pleasure. Thank you, Jake.
Okay, thanks, Jake. Thanks, Dieter. We still have a few minutes left, so if you do have any questions, please submit them using the questions chat box on the right, and we can get you some answers. So we've got a few questions already. First of all, one from the organization point of view, if you wish. So we've been asked if we are going to share a copy of today's webinar, and the answer is yes. We will be sending a recording of the webinar to all the people that have joined the webinar. So you will get a recording within 24 hours. Then we have a questions, I guess, for Dieter. Would Velodyne be able to provide modeling and simulation models for the sensor to enable modeling and simulation of autonomous vehicles?
We are working on several software solutions. I cannot provide details yet, but we can keep into contact and we can provide you more specific information later on.
Okay, thanks. So we have another question on the way that the LiDAR and the INS are paired. So the question is whether we paired, basically whether we inserted a chip scale navigation grade IMU directly onto the LiDAR. So the answer is no. What we have done is, as you have seen from the images perhaps, is literally having the two devices, the LiDAR and the INS, mounting together on a rigid mount, and then calculated the bore sight angles as Jake described, and obviously the relative positions. So we are physically using two separate devices. Another question on the accuracy of the INS is, does the system need a base station for high accuracy? So basically with what Jake described as being RTK position mode. The answer is yes, although it is in a more wider sense. So it doesn't have necessarily to be a field-based station. This can be also NTRIP corrections, or you can also add your corrections data in post-processing only. So you don't need necessarily to have it in real time. You can use RINX files, for example, to improve the position accuracy of the INS data in post-processing. Okay, we've got a question on using visual odometry to support the INS and improve the accuracy. So we are looking at this. We are investigating different solutions to improve the position accuracy of the INS, not just using GNSS, but what we call generic aiding. So that can be different sources, including odometry, including visual odometry. That the aim in doing this is basically to being able to provide a very accurate navigation data in all environments. So not just where the GNSS data is freely available, but also in challenged GNSS environments. Okay, we have got a question on advanced smoothing. Jake showed you an example of how lines can be smoothed in post-processing by using this feature in our software. So we've got a question on whether this will negatively impact the accuracy of the point cloud. So first of all, we have to say that this is only required in poor conditions. This is when you use the combined processing mode. So you improve the accuracy in poor GNSS. And the feature basically helps mitigating the drift of the trajectory. So the general answer is no, you won't have that. So we recommend always to use the combined processing mode when you are in a challenged GNSS environment. This will definitely improve the accuracy. And then on top of the combined processing mode, you can add the advanced smoothing, so you can avoid those little jumps in trajectory that might not be desirable most of cases. Okay, we've got a question on whether a smartphone can be used as a smartphone with a gyroscope can be used as an IMU. So I would say that the quality of the solution would be very different to what you can get using a proper INS. Our systems use a Kalman filter, to put together the IMU data and GNSS data. And also we have the option, as Jake described, using the JX-IX algorithm to tightly couple the IMU and GNSS data, which is something that you won't get simply using the phone. So you definitely cannot expect the same level, or not even close level of accuracy by simply using a smartphone. Okay. We have got questions on the IMUs. It says, what grade of IMU have you been using? So obviously we produce our own IMUs. We have our own production site. If you wanted an idea of the level of accuracy that you can get using our IMUs, you are looking at an accuracy of 0.03 degrees for roll and pitch angles in real time. So that just to give you an idea basically of the level of accuracy from orientation. If you are thinking of the level of drift that you can get in position drift, that is in total absence of GNSS data, so just by using the IMU, you are looking under 10 meters after more than a minute of complete GNSS outage. This will pretty much depend on the actual use case, because it will depend on what kind of motion you will have during the GNSS outage. And if interested, you can go on our website, and we have an example, an article that we created where we tested basically the position drift in different when the IMU is affected, say, by a different period of times of GNSS outage. Okay, then we have a question on the fact that positioning in forest areas is often a problem. Obviously, that is because the GNSS signal can be very challenged in those conditions. So the answer to this is that we use the IMU to help support the GNSS precisely for this reason. So you can compensate for periods of time where you have absence of GNSS signal. So having said that, often the best solution would be to fly over the forest with a UAV, because the LiDAR can penetrate the vegetation canopy, and it will give you, the full details of the canopy, even if surveyed from say the top. You don't have necessarily to go into the forest for your survey. Okay, I'm just looking for some other questions. A question on using multiple laser scanners, and the answer is yes. You can use an INS with a multiple laser scanner LiDAR and georeference the data, all the same, in basically the same way that you would use with another LiDAR. The point cloud will obviously be more dense, and as ever, bore sighting the data bore sighting the INS with the LiDAR is very, very important. Okay, a question on correcting roll orientation error during the bore sight. So our software, XTS Georeferencer, provide a tool for bore sighting, and the bore sight calibration will optimize all three angles, so yaw, pitch, and roll errors. What we are trying to do now, we are developing at the minute the optimization, not just of the orientation angles between the INS and the LiDAR, but also the relative position between them. Our current solution includes for demos, we do not sell that yet, includes a rigid mount that we have designed and built, so we know exactly the relative position of the INS and the LiDAR, but at times the INS and the LiDAR might not necessarily be mounted closely together, so having a possibility of optimizing the lever arms is also important, and we are working on this development currently. Okay. Another questions on the fact that some LiDARs have a degraded accuracy on retroreflectors. So a question is asking basically whether Velodyne is sufficiently robust to be used for bore sight calibration. So before answering this, Dieter might want to comment on this possibly.
Yeah, principally all LiDAR sensors leave the factory finely calibrated, and with regards to sensitivity for retroreflective measurements, the client doesn't need to do any efforts anymore. So once they are calibrated, it is at it is. It depends on the time the sensors are in use. For sure, over a long time, laser diodes can degrade a bit, but principally you can rely on the retroreflectivity measurements, so it does not affect in any way significantly your bore sight calibration.
Okay, thanks, Dieter. And on our side, we can say that we have tested this many times, and we can say that the solution definitely appears to be reliable in detecting the retroreflective threshold for our targets.
Yeah.
So based on our experience, yes, we can confirm that that's the case. Okay, then I guess we have reached now the end of the hour. We just wanted to know that if you have any other questions, you can always submit them to us or to Velodyne, and we will try to get you an answer. As mentioned, we will be sending out a copy of this webinar recording in the next 24 hours. So thanks everyone that joined. Thanks everyone that presented this webinar. I hope you enjoyed it and hope to see you soon on one of our next webinars. Have a good day, everyone.
Yeah, thanks, Sam. Thanks, everybody.
Yeah, thanks also from my side. Goodbye. Take care.